Reliable quantum computing in progress in error correction. On June 19, 2025, a significant milestone in quantum computing was announced by Satya Nadella, CEO of Microsoft, through a tweet that highlighted the introduction of groundbreaking 4D quantum error correction codes. This advancement is regarded as a crucial step toward achieving reliable quantum computing, which requires comprehensive improvements across the entire stack, from error correction to hardware development. The introduction of these codes, which promises to reduce error rates by an impressive factor of 1,000, is expected to bring utility-scale quantum computing closer to realization. Introduction of 4D geometric codes. At the heart of this development are the innovative 4D geometric error correction codes, which have been designed to enhance the reliability and performance of quantum systems. These codes work by distributing quantum information more efficiently across multiple dimensions, thereby improving the overall integrity of data within quantum circuits. This advancement is integrated into Microsoft's Quantum Development Kit and Azure quantum platforms, making it a pivotal component for practical implementations in quantum computing. Error reduction achievements. The introduction of 4D error correction codes is revolutionary, as it addresses one of the most critical challenges in quantum computing: error rates. The codes are engineered to drastically lower logical qubit errors, achieving a reduction in error rates by approximately 1,000 times. This significant decrease is essential for ensuring accurate and dependable quantum computations, which are crucial for various applications in fields such as finance, healthcare, artificial intelligence, and cryptography. Path towards utility-scale quantum computing. The potential implications of these advancements are vast and transformative. Both Satya Nadella's announcement and insights from industry experts, including Josh Cook, emphasize that these innovations mark a crucial turning point in the evolution of quantum computing. They signal a shift from theoretical models to practical applications that can solve real-world problems. The advancements in error correction are positioned as vital for transitioning quantum computing from an experimental phase to a scalable technology capable of being integrated into everyday use. Real-world applications. With the enhanced reliability brought about by the new 4D error correction codes, the prospect of deploying quantum computing in real-world scenarios is becoming more tangible. Industries such as medicine could benefit from faster drug discovery processes, logistics could see improvements in supply chain optimization, artificial intelligence might advance with enhanced data processing capabilities, and cryptography could evolve with stronger security protocols. The advancements imply that quantum computing will not just remain a niche technology but will become an integral part of various sectors, revolutionizing how they operate. Community engagement and collaboration. A noteworthy aspect of this announcement is the collaboration between Microsoft and Atom Computing, which underscores the importance of teamwork in addressing the inherent challenges of quantum computing. This partnership aims to enhance quantum system design and functionality, illustrating that collective efforts are essential for solving the complex problems that have historically hindered progress in this field. The collaboration also reflects a growing trend in the technology sector, where partnerships can accelerate innovation and lead to groundbreaking advancements. Common themes across sources. The significance of the 4D error correction codes and the necessity for comprehensive advancements across the quantum computing stack are themes consistently echoed across various sources. There is a shared optimism that reliable quantum computing is not merely a theoretical concept but is on the verge of becoming a practical reality. The potential for transformative applications across multiple industries is a recurring point of discussion, with many experts highlighting the importance of these advancements in shaping the future of technology. Differences between sources. While the tweet from Satya Nadella provides a succinct overview of the importance of both error correction and hardware improvements, it does not delve deeply into the specific mechanics of the 4D codes. In contrast, Josh Cook's commentary offers a more detailed explanation of the 4D codes, their implications, and how they fit within Microsoft's existing platforms. This divergence in depth reflects the varying perspectives and focuses within the discourse surrounding quantum computing advancements. Conclusion: the strides made in quantum error correction through the implementation of 4D codes are setting the stage for reliable quantum computing with significant prospects for transformative applications across multiple sectors. The collaborative efforts within the industry not only highlight the complexity of the challenges faced but also underscore the necessity for a comprehensive approach to overcoming them. As the quantum computing landscape evolves, the potential for practical utility-scale applications is becoming increasingly evident, promising to reshape the technological landscape for years to come. The content presents significant advancements in quantum computing, particularly focusing on Microsoft's introduction of 4D quantum error correction codes. Here, I will highlight the counterintuitive information present in the content regarding quantum computing and its implications. 1. Error correction versus hardware improvements. It might seem intuitive to focus primarily on hardware advancements to enhance quantum computing capabilities. However, the emphasis on error correction, particularly through the new 4D codes, reveals that software-level improvements can drastically impact performance. This is counter to the usual narrative that hardware is the primary bottleneck in technological advancement. 2. Magnitude of error rate reduction. The claim of reducing error rates by 1,000 times may initially appear exaggerated or overly optimistic. Typically, significant improvements in technology are incremental rather than exponential. This leap suggests that the principles underlying quantum error correction are more effective than previously understood, challenging the notion that progress in quantum computing must always be slow and methodical. 3. Interdependence of components. The assertion that reliable quantum computing requires advancements across the full stack suggests a holistic approach that contradicts the common belief that focusing on one area like hardware or software can yield sufficient improvements. This holistic view emphasizes that innovation in one part of the system can significantly impact the overall performance, pointing to a more interconnected understanding of technology development. 4. Practical applications emerging from theoretical constructs. The transition from theoretical frameworks to practical applications in fields like medicine and artificial intelligence may seem counterintuitive. Historically, many groundbreaking technologies took years or decades to translate from research to real-world applications. However, the rapid progression indicated by the 4D error correction code suggests that the gap between theory and application is narrowing, which could accelerate adoption and innovation. 5. Collaboration as a key driver. The partnership with Atom Computing underlines the counterintuitive idea that collaboration among companies can lead to significant breakthroughs. In a competitive tech landscape, there is often a focus on proprietary advancements. However, this collaboration indicates that pooling resources and expertise can lead to faster and more significant advancements than individual efforts. 6. Public perception of quantum computing. The excitement around utility-scale quantum computing may counter the public perception that quantum computing is a distant or abstract concept. The narrative being constructed around practical applications and imminent breakthroughs challenges the idea that quantum computing is primarily a subject for academic research rather than an impending reality that could soon affect everyday life. 7. Disruption in established fields. The mention of potential breakthroughs in logistics, AI, and cryptography hints at the disruptive nature of quantum computing. Many may believe that established technologies are resilient and would not be easily replaced. However, the implications of reliable quantum computing suggest that industries could be fundamentally transformed much sooner than anticipated, indicating a rapid shift rather than a gradual evolution. These counterintuitive points not only highlight the rapid advancements in quantum computing but also challenge prevailing assumptions about technology development, the interplay between theory and application, and the collaborative nature of innovation. Understanding these subtleties can significantly impact how we approach and anticipate the future of quantum computing and its integration into society. The report on advancements in quantum computing, particularly focusing on the introduction of 4D quantum error correction codes, contains several important elements that are often overlooked by the general audience. Here, I'll identify these key components and explain their significance. 1. 4D geometric codes as a breakthrough in error correction. Many readers may not fully grasp the importance of the 4D geometric codes introduced by Microsoft. The significance of these codes lies in their ability to dramatically reduce logical qubit errors by a factor of 1,000. This is not just a minor improvement, it represents a fundamental shift in how quantum information can be processed and stored. Why it matters. The ability to reduce error rates so significantly is crucial for practical quantum computing applications. Quantum systems are highly susceptible to noise and errors, which can lead to unreliable computations. By addressing this issue with advanced error correction codes, we are moving closer to the reliability needed for real-world applications in fields such as medicine and cryptography. This breakthrough could pave the way for quantum computers to perform complex calculations that are currently impossible with classical computers. 2. The full stack approach. The report emphasizes the importance of progress across the full stack of quantum computing, which includes everything from error correction to hardware. This holistic view is often overlooked because discussions around quantum computing tend to focus on isolated breakthroughs or specific technologies. Why it matters. A full-stack approach is essential because improvements in one area like error correction cannot compensate for deficiencies in another like hardware. For example, even with exceptional error correction, if the hardware is not capable of supporting complex calculations or handling qubit interactions effectively, the overall system will still fail to deliver reliable results. This interconnectedness highlights the complexity of developing practical quantum systems and underscores the collaborative efforts needed across various domains of expertise. 3. Collaboration with atom computing. The partnership with atom computing is a critical detail that may not receive enough attention. Collaborations like this are instrumental in addressing the multifaceted challenges of quantum computing, where expertise in multiple areas is required to innovate effectively. Why it matters. Collaborations can accelerate progress by pooling resources, knowledge, and technologies. The integration of different approaches and perspectives can lead to more robust solutions. This partnership signifies a collective acknowledgement within the industry that solving the challenges of quantum computing requires a cooperative effort rather than isolated advancements from individual companies. 4. Implications for real-world applications. The report touches on various fields where reliable quantum computing could have a transformative impact, such as medicine, logistics, artificial intelligence, and cryptography. While these applications are mentioned, the depth of their potential implications is often not fully explored. Why it matters. Understanding the specific applications of quantum computing is vital for grasping its significance. For instance, in medicine, quantum computers could accelerate drug discovery and personalized medicine by simulating molecular interactions at unprecedented scales. In logistics, optimized routing and supply chain management could lead to significant cost savings and efficiency improvements. Highlighting these applications can foster greater public interest and investment in quantum technologies, as stakeholders begin to see the tangible benefits of these advancements. 5. Transitioning from theoretical to practical use. The report suggests that these advancements are not merely theoretical but are aimed at transitioning quantum computing to utility-scale applications. This transition is often underestimated in discussions about quantum technology. Why it matters. The shift from theory to practical application is where many technological advancements falter. By emphasizing that we are on the cusp of utility-scale quantum computing, the report instills a sense of urgency and excitement about the future of technology. It suggests that we are not far from a time when quantum computing could be integrated into everyday business practices and scientific research, fundamentally altering how we solve complex problems. 6. Community engagement and communication. Finally, the report reflects a broader trend towards community engagement within the quantum computing field. The active communication from key figures like Satya Nadella and Josh Cook is an important aspect that should not be overlooked. Why it matters. Effective communication helps demystify quantum computing for the public and can inspire the next generation of researchers and developers. By sharing advancements and engaging with the community, industry leaders can foster a culture of innovation and collaboration. This is crucial for attracting talent and investment into the field, as well as for ensuring that advancements in quantum technology are aligned with societal needs and ethical considerations. Conclusion. The advancements in quantum computing highlighted in the report, particularly the introduction of 4D geometric error correction codes, represent a significant leap forward in making reliable quantum computing a reality. By focusing on the importance of full-stack development, collaboration, practical applications, and community engagement, we can appreciate the multifaceted nature of this technological evolution. Understanding these elements not only provides insight into the current state of quantum computing but also emphasizes the importance of continued investment in research in this transformative field. 1. Introduction of 4D geometric codes. The introduction of four-dimensional geometric error correction codes by Microsoft represents a pivotal advancement in the reliability of quantum computing. These codes effectively distribute quantum information across the system, which enhances the error correction capabilities significantly. By addressing the fundamental challenges associated with qubit errors, these codes not only improve the performance of quantum systems but also serve as an integral part of Microsoft's Quantum Development Kit and Azure quantum platforms. This innovation is key to transitioning quantum computing from theoretical models to practical applications. 2. Error reduction achievements. The remarkable achievement of reducing logical qubit error rates by a factor of 1.000 through the implementation of 4D codes is a groundbreaking development. This drastic reduction in errors is critical for ensuring that quantum computations can be performed accurately and reliably. As quantum computing aims to solve complex problems that classical computers struggle with, this level of error correction is essential for the technology to be dependable and usable across various industries, marking a significant milestone toward practical quantum applications. 3. Path towards utility-scale quantum computing. The announcement of these advancements signals a crucial step toward utility-scale quantum computing. As highlighted by both Satya Nadella and Josh Cook, the implications of 4D error correction codes extend beyond theoretical advancements. They are positioned to enable real-world applications in diverse fields such as medicine, logistics, artificial intelligence, and cryptography. This shift from experimental to practical implementation represents a transformative potential for industries reliant on complex computational capabilities, showcasing the broader impact of reliable quantum computing. 4. Community engagement and collaboration. The collaboration between Microsoft and Atom Computing underscores the importance of collective efforts in overcoming the challenges of quantum computing. This partnership demonstrates a strategic approach to enhancing quantum system design and functionality, emphasizing that progress in quantum technology is not solely dependent on individual companies but requires a community-driven effort. The engagement of various stakeholders in the quantum ecosystem is vital for addressing the multifaceted challenges and accelerating the development of scalable solutions, ultimately leading to a more robust quantum computing framework. In summary, the introduction of 4D geometric codes, significant reductions in error rates, pathways to utility-scale applications, and collaborative efforts within the quantum community are critical points for analysis and discussion in the ongoing evolution of reliable quantum computing. These elements not only highlight the technological advancements being made but also the broader implications for various sectors and the collaborative spirit required to realize the full potential of quantum technologies. 1. The Manhattan Project 1942–1946. The Manhattan Project is a historical case that exemplifies the need for comprehensive advancements in technology to achieve a significant breakthrough, in this case the development of the atomic bomb. This project required collaboration among various scientific disciplines including physics, engineering, and metallurgy, as well as advancements in materials instrumentation and theoretical understanding. The successful development of nuclear weapons represented a monumental leap in both scientific understanding and technological capability. Similar to the recent strides being made in quantum computing with error correction and hardware advancements. 2. The Apollo Program 1961–1972. The Apollo program is another historical example of a full-stack technological advancement leading to a critical achievement, in this case landing humans on the moon. This program required innovations in various fields including materials science, avionics, computer engineering, notably the development of onboard computers and extensive error correction measures in navigation and control systems. Just as the Apollo program advanced space exploration through interdisciplinary collaboration and rigorous testing, the current efforts in quantum computing focus on integrating various technological components to achieve reliable and practical quantum systems. 3. The Human Genome Project 1990–2003. The Human Genome Project represents a significant collaborative effort in the field of genetics and biotechnology aiming to map and understand all the genes of the human species. This project required advancements across the entire spectrum of genomics, including sequencing technology, bioinformatics, and data management. The collaborative nature of the Human Genome Project involving multiple institutions and disciplines mirrors the contemporary efforts in quantum computing to collaborate across various sectors from hardware development to software and error correction to achieve practical applications in fields such as medicine and artificial intelligence. Future outlook on quantum computing. As we look towards the future of quantum computing, particularly following recent advancements such as Microsoft's introduction of 4D quantum error correction codes, several key predictions can be made regarding the trajectory of this technology and its implications across various industries. 1. Increased reliability and practicality. The development of 4D error correction codes, which promise to reduce error rates by a staggering factor of 1,000, is a game-changer for the reliability of quantum computers. This significant leap in error correction will likely lead to more stable and reliable quantum systems, making practical applications feasible within the next decade. As these technologies evolve, we can expect to see quantum computers being utilized for complex problem-solving tasks that were previously unimaginable. 2. Utility-scale quantum computing. With advancements in error correction and hardware integration, we anticipate a shift from experimental quantum computing to utility-scale solutions. This transition is projected to happen within the next 5 to 10 years, allowing businesses and researchers to harness quantum computing for real-world applications. Industries such as pharmaceuticals, logistics, and artificial intelligence will be among the first to benefit from these developments, enabling breakthroughs in drug discovery, optimization of supply chains, and advanced machine learning models. 3. Collaboration and ecosystem development. The collaboration between tech giants like Microsoft and specialized companies like Atom Computing will be crucial in accelerating the development of quantum technologies. As these partnerships deepen, we predict a growing ecosystem of startups and established companies focusing on quantum applications, tools, and services. This collaborative environment will foster innovation and lead to the emergence of new business models centered around quantum capabilities. 4. Integration with classical computing. The future of quantum computing will not exist in isolation. Instead, we foresee an increasing integration of quantum and classical computing systems. Hybrid models that combine quantum processors with classical architectures will likely become the norm, allowing for enhanced computational power and efficiency. This integration will also help address the challenges of quantum programming and algorithm development, making it easier for developers to create applications that leverage both computational paradigms. 5. Expansion of quantum algorithms and applications. As quantum computing matures, we expect the development of a new class of quantum algorithms tailored for specific industries. These algorithms will capitalize on the unique capabilities of quantum systems, such as superposition and entanglement, to solve problems that are currently intractable for classical computers. Applications in cryptography, financial modeling, materials science, and machine learning are just a few areas where quantum algorithms will make a significant impact. 6. Regulatory and ethical considerations. As quantum computing becomes more prevalent, we anticipate heightened scrutiny regarding its ethical implications and regulatory frameworks. Concerns about data security, particularly in relation to quantum cryptography, will lead to the establishment of guidelines and standards to govern the use of quantum technologies. Policymakers will need to work closely with technologists to ensure that the benefits of quantum computing are realized while mitigating potential risks. 7. Educational and workforce development. To support the growth of the quantum computing sector, there will be an increasing focus on education and workforce development. Academic institutions will likely expand their curricula to include quantum computing principles, leading to a new generation of professionals equipped with the skills needed to advance the field. Specialized training programs and online courses will also emerge, making quantum education more accessible to a broader audience. 8. Global competition and collaboration. Finally, the race for quantum supremacy will continue to be a focal point for nations around the world. Countries will invest heavily in quantum research and development, leading to a competitive landscape that could spur innovation. However, we may also see increased international collaboration as the global scientific community recognizes the benefits of sharing knowledge and resources in advancing quantum technologies. Conclusion. The future of quantum computing is poised to be transformative, driven by significant advancements in error correction, hardware integration, and collaborative efforts across the industry. As we move closer to utility-scale quantum systems, the implications for various sectors are profound, promising to reshape our approach to complex problems and unlock new possibilities. This journey, while filled with challenges, will ultimately pave the way for a new era of computing that enhances our capabilities and drives economic growth.